Hi, welcome back. Let's take a look at some chemical equilibrium questions. The question reads, the diagram below represents a mixture of NO2 and N2O4 molecules at equilibrium in a 1 dm cube container at T degrees Celsius. The balance equation is given. Which one of the following is true for the value of the equilibrium constant Kc? Okay, now in this kind of question, it's quite unusual that we're given a diagram like this, but actually what we need to do is we need to count. So we'll count the molecules of N2O4 and then we'll count the molecules of NO2. So the molecules for N2O4, there's 1, 2, 3, 4, 5, 6. So for N2O4, we can calculate the concentration. The concentration will be number of moles divided by volume. There's 6 and the volume is 1. So that's 6 dm cubed. Sorry, 6 moles per dm cubed. And for NO2, we can do the same thing. So we can count it if we want. That's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So concentration is equal to number of moles divided by volume, 12 divided by 1, which is 12 moles per dm cubed. And now we can calculate Kc. Kc is equal to concentration of N2O4, and that's going to be to the power of 1 divided by the concentration of NO2 to the power of 2. Now N2O4 was 6, so 6 to the power of 1 divided by NO2 was 12, 12 to the power of 2. Now, we don't need to really do any calculation here, though we can do this in a calculator. But when we do get the answer, we'll find that the answer is between 0 and 1. That's mainly because the numerator is smaller than the denominator. And so the value is going to be between 0 and 1. Okay, let's look at this question, 1.6, which is a little bit of a tricky question. A reaction is at equilibrium in a closed container according to the following balanced equation. The volume of the container is now increased while the temperature remains constant. A new equilibrium is reached. Which one of the following combinations is correct for the new equilibrium? Okay, so if the volume increases, that means the pressure will decrease. Now, according to Le Chatelier's principle, if pressure decreases, the system wants to increase the pressure. Now, when we speaking about increasing pressure, how does the system do that? So the system will favor the side with more molecules. Now be careful. In this case, we are going to exclude the solids. So on the left hand side we have 0 and on the right hand side we have 1. So in this case the forward reaction is favored. Right? Now since the forward reaction is favored, the number of moles of O2 will increase. Okay, so we are currently with option C or D. Okay, now let's decide on what happens to Kc. Now since the only thing that was changed was the volume, remember temperature stayed the same, Kc will not change. Right, remember the only factor that affects Kc is temperature. So Kc is affected by temperature. So in this case, since the temperature was the same, Kc was unchanged. So still, we are stuck with option C or D. Now, let's look at how we can figure out what happens to the concentration of O2. Now, this is the tricky part because not many people would think of it. What we need to do here is if we look at the Kc expression, the Kc expression is only going to be the concentration of O2 because solids don't have a concentration. So they are excluded from the Kc expression. Since the Kc is unchanged, it means that the concentration of O2 must also be unchanged. And so the answer to this question is going to be C. All right, let's move on. Question number 6. Consider the following hypothetical reaction reaching equilibrium in a 4 dm cubed closed container at 150 degrees Celsius. So 2AB producing A2 plus B2. The graph below shows the changes in the amounts of reactants and products over time. We'll jump to question 6.3. A change was made to the equilibrium mixture at T equals 80 seconds. So T equals 80 seconds. Here, something changed. All right, now if I'm following these graphs, I can see that, okay, there's something here. So that was the change. Now they want to know, what is that change? Write down the change. So you can see at 80 seconds, there was a sharp spike in the number of moles of A2. And so that's our answer. So 6.3.1, what happened is that A2 was added. Okay? Next question reads, explain or use Le Chatelier's principle to explain how the system reacts. So 6.3.2, if the amount of A2 increases, the system wants to decrease the amount of A2. The system does this by favoring the reverse reaction. Now, if the reverse reaction is favored, it means that the amount, or we can say rather the number of moles of AB will increase and the number of moles of B2 will decrease. Okay, move on. Question 6.4, calculate the equilibrium constant Kc at T equals 120 seconds. Okay, let's first write out our Kc expression. So Kc is equal to the concentration of products. In this case, my products are A2 and B2 divided by reactants, which is AB, and the coefficient is 2, which means we make it into an exponent. Next, we need to work out our concentrations. Well, at T equals 120 seconds, we can read the number of moles from the graph. So there, then 120 seconds is here, and 120 seconds is here. Now, for A2, it's 8 moles. And remember, they told us that the container is a 4 dm cubed container. So 8 divided by 4. Then for B2, it's going to be 2 divided by 4. And then lastly, for AB, it's going to be 10 divided by 4 all squared. And we substitute that and put that into our calculator. We get a Kc value of 0.16. Okay, question 6.5. At T equals 130 seconds, the temperature of the system is decreased to 100 degrees Celsius. Draw a potential energy diagram for this reaction. Now, potential energy diagram looks like this. But what we don't know is if this reaction is exothermic or endothermic. Now, to do that, we need to see what happened to the number of moles and then figure out whether it's exothermic or endothermic. So at t equals 130, at t equals 130, what happened? Let's draw a line. So 130 is here. So here, what happened? So AB increased, A2 decreased, and B2 decreased. So in other words, we can say, let's make a note on the side here, that the products decreased. Decreased, reactant increased. So that must mean that my reverse reaction was favored. Okay. So they tell me that the temperature decreased. So remember, a decrease in temperature favors the exothermic reaction. Now, if the reverse reaction was favored, that means the reverse reaction must be exothermic. Which means that the forward must be endothermic. How do I draw an endothermic? Endothermic will look like this. Okay? Now, question 6.5.2, will the equilibrium constant Kc at 100 degrees be greater than, less than, or equal to the Kc at 150 degrees? Explain your answer. All right. So we can see that the concentration of AB increased. The concentration of A2 and B2 decreased. So we can use this. We can see that the products got smaller, the reactants got bigger. Now remember, Kc is equal to concentration of products divided by concentration of reactants. Since the products got smaller and reactants got bigger, it means that the Kc value will decrease. Remember, if you have a fraction and your numerator gets smaller or your denominator gets bigger, then the value of that fraction will decrease. Okay? Next question, question 6.6. So this is 6.5.2, and then question 6.6. The initial reaction now takes place in the presence of a catalyst. Describe the changes that will be observed in the graph between t equals 0 and t equals 60. Now, a catalyst does nothing to the number of moles, right? So all the catalyst is going to do is that the catalyst is going to increase the rate of both the forward and reverse reaction. Now, how will that look on this graph? So basically, we can see now, if we follow our original graph, we can see that equilibrium is reached at about 40 seconds. Now, when a catalyst is used, the equilibrium will be reached in a shorter time. So equilibrium will be reached less than 40 seconds. So new equilibrium reached in less than 40 seconds. That's all it does. It speeds up the reaction. So if the equilibrium was reached in 40 seconds without a catalyst, then with the catalyst, it's going to reach equilibrium in less than 40 seconds. Okay? So that's it for this paper, for this question. And I hope you found it useful. If you did, please leave a like, share, subscribe, hit that bell icon. And if there's something specific you want to know, let me know in the comments below. And until the next one.